The ground vibrates slightly under your feet. The steel wheels glide along the rails with a steady metallic rhythm. Hundreds of tons of steel move forward with surprising smoothness and stability. At first glance, nothing about this seems mysterious. Trains stay on tracks. That's what they are designed to do. But if you slow down and think about it carefully, the situation becomes more puzzling than it first appears. A train can weigh hundreds or even thousands of tons. Yet all that weight is supported by thin steel wheels resting on narrow steel rails. The contact area between the wheel and the rail is actually very small, often only a patch about the size of a coin. And despite this tiny contact area, the train moves safely at high speeds, sometimes faster than 300 kilometers per hour in modern high-speed rail systems. So a simple question begins to form. Why doesn't the train slide off the track? The rails don't surround the wheels. They don't lock the train in place the way a groove holds a sliding door. The wheels simply sit on top of the rails. Gravity pushes them downward, but nothing obvious seems to stop them from slipping sideways. This kind of question is exactly the type that fascinated the physicist Richard Feynman. He often enjoyed taking something extremely ordinary and asking a deceptively simple question about it, something everyone assumes they understand. Then, when people try to explain it, they discover that their understanding isn't quite as complete as they thought. If you ask most people why trains stay on the track, they usually give the same answer. They say it's because of the small ridge on the inside edge of the wheel. If you look closely at a train wheel, you'll notice that it isn't flat like a car tire. Each wheel has a small vertical lip on one side. Engineers call this ridge a flange. The flange appears to wrap around the rail slightly. Because of that shape, it seems obvious that the flange is what keeps the train from slipping off the track. It acts like a barrier that blocks sideways movement. At first, this explanation feels completely satisfying. But if you examine the physics a little more carefully, something strange appears. In normal motion, the flange almost never touches the rail. If it did, trains would constantly produce loud grinding sounds as metal scraped against metal. The friction would be enormous. The wheels and rails would wear out extremely quickly. Instead, when trains move smoothly along straight tracks, the flange usually floats just a few millimeters away from the rail. It is there as a safety feature, not the primary steering mechanism. That realization creates a small but interesting mystery. If the flange isn't normally touching the rail, then it isn't actually holding the train in place. Most of the time, the wheels are simply rolling on top of the rails without any side barrier. So now the question becomes even more interesting. If nothing is physically gripping the rail from the side, why does the train remain centered on the track instead of drifting sideways? This is the point where the simple explanation begins to fall apart and the real physics begins to appear. And when students first encounter the true answer, many of them feel a moment of genuine surprise. Something that seemed mechanically obvious turns out to depend on a subtle geometric trick hidden in the shape of the wheels themselves. The real explanation begins with something so subtle that most people never notice it, even if they stand next to a train and look directly at the wheels. Train wheels are not perfectly cylindrical. If you imagine a normal wheel like the tires on a car, you would picture a cylinder. The diameter of the wheel is exactly the same from one side to the other. No matter where the wheel touches the road, the radius remains constant. Train wheels are different. Instead of being perfectly cylindrical, they are slightly conical. This means the surface of the wheel is shaped like a very gentle cone. One side of the wheel has a slightly larger diameter than the other side. The difference is extremely small. If you saw the wheel quickly, you might not notice anything unusual at all. But that tiny change in shape plays a crucial role in keeping the train centered on the rails. To understand why this matters, imagine two train wheels connected by a solid axle. Unlike the wheels of a car, train wheels on the same axle are fixed together. They cannot rotate independently. When one wheel turns, the other wheel must turn at exactly the same rate. This is an important detail, because it means the wheels cannot adjust their speeds separately when the train moves sideways. Now imagine the train drifting slightly toward the left side of the track. At first, this sideways movement is extremely small, maybe just a few millimeters. But because the wheels are conical, that tiny shift changes where each wheel touches the rail. The wheel on the left side of the axle moves toward the narrower part of the cone. That means the effective radius of the wheel becomes slightly smaller. At the same time, the wheel on the right side moves toward the wider part of the cone. That means its effective radius becomes slightly larger. So suddenly something interesting happens. Both wheels are still rotating at exactly the same speed because they are connected by the axle. But one wheel now has a larger radius than the other. And when a wheel has a larger radius, it travels a slightly greater distance with each rotation. This means the right wheel now wants to move forward slightly faster than the left wheel. But because the wheels are connected, the system cannot move straight ahead in that configuration. Instead, the difference in distance forces the axle to turn slightly. That turning motion gently steers the train back toward the center of the track. In other words, the geometry of the wheels automatically corrects sideways drift. If the train drifts left, the shape of the wheels causes it to steer right. If the train drifts right, the opposite effect occurs and the train steers left. The system constantly nudges itself back toward the middle. What makes this mechanism remarkable is that it requires no sensors, no electronics, and no active control. The physics of the system performs the correction automatically. This idea is sometimes called self-centering stability. The train does not stay on the track because something is tightly holding it there. It stays centered because the shape of the wheels continuously converts sideways motion into steering motion. The moment the train begins to drift, the geometry of the wheels produces a restoring effect. And this restoring effect happens smoothly and continuously as the train moves. It is a quiet piece of engineering that works so reliably that most passengers never realize it exists. Yet hidden inside the simple shape of those steel wheels is a clever use of geometry that allows a machine weighing hundreds of tons to balance itself on two narrow rails while moving at high speed. Once you understand the conical shape of train wheels, something remarkable becomes clear. The train does not simply sit on the rails and hope to remain centered. Instead, the entire system quietly corrects itself every time it begins to drift. Imagine again that the train shifts slightly toward the left side of the track. The shift might be so small that passengers inside the train never notice it. But at the level of the wheels and rails, the geometry immediately begins to respond. Because the wheels are conical, the left wheel now rolls on a slightly smaller radius, while the right wheel rolls on a slightly larger radius. Since both wheels are locked together by a solid axle, they must rotate at the same speed. That constraint forces the system to react. The wheel with the larger radius tries to travel a little farther with each rotation. The wheel with the smaller radius tries to travel a little less. The only way the system can satisfy both conditions at the same time is by gently steering the axle back toward the center of the track. The correction happens automatically. No one inside the train is turning a steering wheel. No computer is calculating adjustments. The system responds purely through the interaction between geometry and motion. This kind of behavior is known as passive stability. Passive stability means a system naturally returns to a stable position without external control. The physics of the system itself pushes it back toward equilibrium whenever it drifts away. You can see a simple example of this idea if you place a marble in a shallow bowl. If you push the marble slightly to one side, it rolls back toward the center. The shape of the bowl creates a restoring force. But if you place the marble on top of an upside-down bowl, the situation changes completely. Even the smallest disturbance causes the marble to roll away. The system is unstable. Train wheels are designed so that the rails behave more like the inside of the bowl than the outside. When the train drifts sideways, the geometry creates a restoring motion that nudges it back toward the middle. This design works so well that trains can travel long distances while remaining smoothly centered on the rails. Yet the story becomes more interesting when we consider motion at higher speeds. At moderate speeds, the self-centering behavior keeps the train stable. Small disturbances quickly disappear as the geometry corrects them. But as the speed increases, something unexpected can begin to happen. Instead of smoothly returning to the center, the train may begin to move slightly from side to side. The motion is subtle at first, almost like a gentle weaving. The train drifts a little left, then a little right, then back again. Engineers call this motion hunting oscillation. The same geometry that normally stabilizes the train can sometimes produce a repeating sideways movement when the speed becomes high enough. Tiny imperfections in the rails, small variations in friction, and the flexibility of the suspension system can amplify these oscillations. The train begins to hunt for the center of the track, moving back and forth around it. This does not usually mean the train is in danger. Modern railway engineering carefully controls these dynamics through wheel design, suspension systems, and precise track construction. But understanding this behavior requires deeper physics. Now the problem involves vibrations, friction, and complex interactions between moving parts. The system becomes a dynamic one, where stability depends not only on shape but also on speed and energy. This is one reason railway engineering remains an active field of research even today. Designing trains that travel safely at extremely high speeds requires careful attention to these subtle mechanical effects. What began as a simple question about why trains stay on the track turns out to involve geometry, motion, stability, and dynamic oscillations. And this is often how physics works. A familiar everyday phenomenon opens a doorway into layers of deeper understanding once we begin examining it closely. When the speed of a train increases, the situation becomes more complicated than the simple self-centering picture. At low and moderate speeds, the geometry of the conical wheels quietly keeps the train aligned with the track. Small disturbances appear and disappear without anyone noticing. The system corrects itself almost instantly. But as the speed grows larger, something subtle begins to change. Any real railway track contains tiny imperfections. Even the most carefully engineered rails are not perfectly straight. There are microscopic variations in shape, small differences in rail height, slight irregularities in the surface of the metal. Under normal conditions, these imperfections are too small to matter. Yet when a train moves very fast, even tiny disturbances can start interacting with the natural motion of the wheel system. Imagine pushing a child on a swing. If you push randomly, the swing barely moves. But if your pushes happen at the right rhythm, each push adds a little more energy to the motion. The swing begins to move farther and farther. Something similar can happen with trains. When the train shifts slightly to one side, the conical wheels steer it back toward the center. But because the train is moving quickly, the correction can overshoot slightly. Instead of stopping exactly in the middle, the system may drift a little to the other side. Then the geometry corrects again. Left, right, left, right. A repeating pattern begins to appear. Engineers call this motion hunting oscillation. The train begins to weave gently along the track as it searches for the perfect center position. At first, the movement is extremely small. Passengers usually do not notice it. But as the speed increases further, the oscillation can become stronger. The system now behaves like a mechanical oscillator. Energy moves back and forth between sideways motion and steering correction. Friction between the wheels and rails influences how the motion grows or fades. The suspension system of the train also plays an important role, absorbing some of the energy while allowing some motion to continue. This turns a simple geometry problem into a complex physics problem involving dynamics. Engineers must carefully design the entire system to control these oscillations. Wheel profiles are shaped with great precision. The stiffness of the suspension is tuned to absorb unwanted motion. Tracks are built with strict tolerances to minimize irregularities. Modern high-speed trains represent an extraordinary balance between many physical effects. The wheels must guide the train smoothly along the rails. The suspension must absorb vibrations without making the system unstable. The rails themselves must remain strong and precisely aligned despite temperature changes, heavy loads, and years of use. All of these elements interact. The stability of the train does not come from one single part. It emerges from the cooperation of geometry, friction, motion, and structural design. This is why railway engineering remains an active area of research even today. As trains move faster and faster, engineers must understand these subtle physical interactions with increasing precision. What appears to passengers as a smooth and effortless ride is actually the result of thousands of careful design choices guided by physics. And this realization reveals something interesting about the nature of many technological systems. The systems we rely on every day often work because their designers have learned how to cooperate with the laws of physics rather than fight against them. Instead of forcing stability through heavy control systems, engineers often shape the structure of a machine so that stability emerges naturally. In the case of trains, a simple geometric detail in the wheels allows hundreds of tons of moving steel to guide itself along two narrow rails with remarkable reliability. What begins as a simple question about why trains stay on the track gradually unfolds into a rich story about motion, stability, and the delicate balance between forces and geometry that governs the behavior of machines moving through the physical world. When students first hear the question, "How do trains stay on the track?" they usually expect a simple mechanical answer, something obvious, something visible. Most people immediately think of the flange on the inside of the wheel and assume that it must be doing the job. The flange looks like a guard that wraps around the rail, so it feels natural to believe that it physically holds the train in place. But once the real explanation begins to unfold, the situation becomes more surprising. The flange is not the main mechanism keeping the train centered. Most of the time it is not even touching the rail. Instead, the stability of the train comes from the subtle geometry of the wheels themselves and the way those wheels interact with the rails during motion. For many students, this realization creates a small moment of intellectual discomfort. The explanation they believed was correct turns out to be incomplete. The true mechanism is hidden in something they had never noticed before, the conical shape of the wheels and the rigid axle connecting them. This kind of surprise is common in physics. Our intuition about how the world works is built from everyday experience. We interact with objects, push them, carry them, and observe their behavior. Over time, our brains develop simple mental models that allow us to predict what will happen next. These models are useful, but they are not always accurate. The world often operates according to rules that are more subtle than our first impressions suggest. Systems can maintain stability not because something is actively holding them in place, but because the structure of the system naturally corrects small disturbances. Trains are a perfect example of this idea. Nothing in the system is constantly steering the train. There is no driver adjusting a wheel to keep it centered. Instead, the geometry of the wheels quietly converts sideways motion into steering motion. Every tiny drift automatically triggers a correction. This kind of behavior appears in many physical systems. Consider a spinning top. When a top spins quickly, it remains upright. If you gently push it, the top does not simply fall over. Instead, it begins to wobble in a circular motion called precession. The rotation of the top creates stability through the laws of angular momentum. Another example is a bicycle. When a bicycle moves forward, it becomes much easier to balance. The combination of wheel rotation, steering geometry, and forward motion creates a dynamic system that tends to remain upright. The rider still participates in the balancing process, but the physics of the bicycle plays a large role. In both cases, stability emerges from motion and structure rather than from rigid support. Trains rely on a similar principle. The wheels and rails form a system that naturally steers itself toward balance. The conical shape of the wheels ensures that any sideways drift changes the rolling radius of the wheels, and that difference in radius produces a restoring motion. What makes this idea powerful is that it does not depend on complicated machinery. The stability is built directly into the shape of the system. Once you understand this, you begin to see the same design philosophy appearing in many areas of engineering. Engineers often try to design systems where stability arises naturally from the physical structure of the machine. When the geometry is correct, the system behaves predictably without constant intervention. The success of railway systems over the past 2 centuries is partly due to this elegant simplicity. A train can carry enormous weight across vast distances while relying on a surprisingly small set of mechanical principles. What initially appears to be a simple machine, a pair of steel wheels rolling along steel rails, turns out to be a carefully balanced interaction between shape, motion, and physical law. Understanding how trains stay on the track reveals something deeper about the relationship between engineering and physics. At first glance, a railway system appears simple: two steel rails, a set of wheels, and a long line of connected cars moving from one place to another. Yet behind this apparent simplicity lies a remarkable example of how carefully designed structures can harness the laws of motion. The interaction between wheel and rail is not just a matter of contact. It is a dynamic relationship shaped by geometry, friction, speed, and mass. Every part of the system contributes to the overall stability: the conical shape of the wheels, the rigid axle connecting them, the spacing between the rails, and even the suspension of the train cars all work together to produce smooth motion. When a train begins moving, the wheels roll along the rails with very little resistance. Steel on steel produces surprisingly low friction compared to many other materials. This low friction is one of the main reasons trains are so efficient for transporting heavy loads. A single locomotive can pull thousands of tons of cargo because the wheels roll rather than slide. However, this same low friction could make the system unstable if it were not carefully designed. Without a guiding mechanism, the train might easily drift from side to side. The conical shape of the wheel solves this problem in an elegant way. By changing the rolling radius of each wheel, when the axle shifts sideways, the system converts lateral motion into a gentle steering effect that guides the train back toward the center of the track. This constant process of tiny corrections happens continuously as the train moves forward. Most of the time, these corrections are so small that they are invisible to passengers. The train feels steady, gliding smoothly along the rails. Beneath that calm motion, however, the wheel-rail system is constantly adjusting itself, responding to small variations in track alignment and surface conditions. Engineers must think carefully about these interactions when designing railway systems. The wheels cannot be shaped too steeply, or the steering effect would become too strong and lead to instability at high speeds. If the wheels were completely flat, on the other hand, the self-centering behavior would disappear and the train would rely much more heavily on the flanges pressing against the rails. The track itself must also meet strict standards. Rails are carefully aligned and supported by sleepers and ballast to maintain consistent spacing and smooth surfaces. Even small deviations can influence how the wheels interact with the rails, especially when trains travel at very high speeds. Modern high-speed rail systems require an even greater level of precision. As speeds increase, dynamic forces become stronger and small irregularities can produce noticeable vibrations. Engineers use advanced modeling, testing, and monitoring systems to ensure that both trains and tracks operate safely under these demanding conditions. All of this reveals a powerful idea about technological design. Many successful machines do not rely solely on active control systems. Instead, their stability is built directly into their physical structure. By shaping components in certain ways, engineers can create systems that naturally guide themselves towards stable behavior. The railway wheel is a classic example of this principle. A small geometric detail, the slight cone shape of the wheel, allows an enormous machine to move across long distances while remaining reliably centered on two narrow rails. What seems like a straightforward mechanical arrangement is actually the result of centuries of observation, experimentation, and refinement. The system works not because it resists the laws of physics, but because it uses those laws in a carefully balanced way. In the end, the stability of a train on its track is not maintained by force alone. It emerges from the quiet cooperation between shape, motion, and the fundamental principles that govern how objects move through the world. Looking closely at the railway system also reveals how small design choices can influence the behavior of extremely large machines. A train may weigh hundreds or even thousands of tons, yet its stability depends on details that are measured in millimeters. The shape of the wheel, the distance between the rails, and the angle of contact between metal surfaces all play a role in determining how the system behaves as it moves. One important aspect of this interaction is the way forces are distributed between the wheel and the rail. When the wheel rolls along the rail, the contact area between the two pieces of steel is actually very small. It is not a wide surface pressing down evenly. Instead, the contact occurs over a tiny patch where enormous pressure is concentrated. Despite this pressure, the materials are strong enough to withstand the load repeatedly without failing. Within this small contact region, friction and deformation occur on a microscopic scale. The metal surfaces are not perfectly smooth. Tiny irregularities and elastic deformations allow the wheel to grip the rail just enough to transmit forces without slipping excessively. This grip allows the locomotive to pull the train forward and also allows braking forces to slow the train when needed. At the same time, the rolling motion keeps energy losses relatively low. Because the wheels rotate rather than slide, very little energy is wasted as heat. This efficiency is one of the reasons rail transport has remained so important for both passengers and freight. Large amounts of cargo can be moved over long distances while using far less fuel than many other transportation methods. The shape of the wheels continues to guide the train during this motion. As the axle drifts slightly from side to side, the difference in rolling radius between the two wheels gently redirects the train toward the center of the track. These constant adjustments happen automatically as long as the train is moving forward. Another interesting feature of railway design is the slight inward tilt of the rails, often called rail cant. Instead of standing perfectly vertical, the rails lean inward by a small angle. This tilt helps the wheel tread make better contact with the rail surface and improves the stability of the wheel-rail interaction. It also helps distribute forces more evenly across the wheel surface, reducing wear over time. Curved sections of track introduce additional considerations. When a train moves around a curve, centrifugal forces push the train outward. Engineers compensate for this by raising the outer rail slightly higher than the inner rail, a design known as superelevation. This tilting of the track allows part of the train's weight to counteract the outward force, making the ride smoother and reducing stress on both the train and the rails. All of these design elements work together to create a transportation system that is both stable and efficient. The train wheels, rails, and supporting structures form a carefully balanced network of components. Each piece influences the behavior of the others. The success of railway systems over more than a century demonstrates how powerful simple physical principles can be when they are applied thoughtfully. Engineers do not always need complicated mechanisms to solve difficult problems. Sometimes the most effective solution comes from understanding the natural tendencies of motion and designing structures that guide those tendencies in useful ways. When a train glides along the track, passengers may only notice the scenery passing by outside the window. Yet beneath that quiet motion is a complex interaction of forces, materials, and geometry. The wheels roll, tiny corrections occur, and the system continually maintains its balance. What appears effortless from the outside is actually a remarkable demonstration of how carefully designed machines can work in harmony with the laws of physics.